So today we're going to be talking about combining generative modeling families. Let's look again at the various generative modeling tasks and generative modeling families that we have been looking at this semester, and today we're going to see how we can combine everything that we studied during the class in some new and interesting ways. So first of all, remember that from the beginning of the class until now, we focused our attention on different types of generative models and different types of tasks that are important and useful and that are part of the field of generative modeling. The first task that we looked at was generation. In generation, I guess if you follow this picture, the task of generation is given a data set of, say, images. We want to generate new images which look like the one in our training set. Or if not images, then this could be text, molecules, anything. And we started by deriving autoregressive models as a way of doing generation. And then over the course of the class, we introduced many other modeling families which are effective at generation. In fact, all of them can do generation, but for some of them it's particularly easy. So I would say latent variable models, GANs, score-based and diffusion models. These are all types of models that are very easily suited to generation. Of course, generation is not the only task that we might be interested in. There's also density estimation, which in its most general form consists in trying to recover the data distribution using our model distribution by minimizing some kind of objective, which is typically the KL divergence, which means that it's equivalent to maximizing the log likelihood. And so just simply estimating the density is an interesting task that we looked at specifically when we defined autoregressive models and when we worked with normalizing flows. A lot of those lectures were about how to compute densities, how to compute the log likelihood, and therefore minimize the KL divergence using certain modeling families. And as I explained in a few previous lectures, not every model is well suited to density estimation. Ones that are particularly good are autoregressive models. Normalizing flows are very effective, or they give you exact densities. But actually, for most other modeling families, such as latent variable models or GANs or score-based models, it's not obvious how to get an accurate estimate of log likelihood. So density estimation is another task, and certain models are better suited for density estimation. And finally, there's also the task of representational learning, which is really important. And latent variable models we proposed and introduced them with the goal of doing representational learning, but there's other models which are not as good as latent variable models. They're not by themselves suitable for representational learning. So again, the high-level takeaway from the slide is that there's many different types of models that exist. Some of these models are better at certain tasks than others. The question that I want to look at in this course is, can we combine these different families to get new types of models that get the benefits of each modeling family? So can we get the best of all worlds by trying to combine these different model classes? And so this lecture will be an overview of several papers from the last 6 or 7 years in generative modeling. And these papers all try to combine different ideas from different model families in new ways. And so there's going to be, I guess we will look at ways of combining autoregressive models, VEs, flows, diffusion models, GANs, and I'll introduce several examples of how they can be, or how they have been combined in the past in the literature. So this is not meant to be an exhaustive overview of all the literature on combining generative models that's out there. The goal is to give you some ideas for how all of the models we've seen in this course can serve as building blocks for even more interesting models and how you can solve them, how you can use them to solve new problems that require going beyond just the basic models that we have seen. And also, as you're doing your projects, you might also be interested in exploring new algorithmic ideas, new ways of combining the basic building blocks that we've seen in the class. So these examples, maybe they can be useful to you as inspiration for new ideas to try in your projects. So that's the goal. So as a warm-up, let's start with one simple approach to combining two model families that we have seen at the beginning of the class, which are autoregressive models and variational autoencoders. So if you remember, we introduced autoregressive models at the very beginning, and they're really effective at density estimation and generation. But they don't necessarily have any latent variables. Therefore, they might not be effective at representational learning. Can we combine ideas from latent variable models, which can do representational learning, with autoregressive models and try to get the best of both worlds? So this would be my first example. So first, let's do a quick recap on what is a latent variable model. So in a latent variable model, we typically have two sets of variables, z and x, and we use a neural net to parameterize a mapping between the latent variable and the observed variable. So one example in which, well, one way that we have seen to do this is using a deep Gaussian model, or in fact, this picture can also represent the process that's used in a GAN. So we have a latent variable z, it maps to an observed variable x, and there is some neural net that will take a vector of z's. We call that z here is a vector. It's a distributed representation for the latent variable. It's a distributed vector valued embedding, and it's a distributed representation for the data x that we're trying to model. So we're going to take this vector z and pass it through a neural net, and the neural net will either spit out directly an image x, in which case we have something which looks like the generator of a GAN, or it could spit out the parameters of a distribution, for example, a Gaussian distribution over x, which might look like this, right? So this could be either directly the image or a distribution over the image. So this is the type of model we used in variational autoencoders. If we use variational autoencoders, then we set a prior P of z, and then we specify the posterior distribution. We specify the likelihood of x given z, the probability of x given z, using. We specify it to be a normal distribution with a mean and variance that is parameterized by a neural net, which is a function of z. Now this defines a joint distribution. The product of t of z and t of x given z defines a joint of x and z. And we can fit it to the data using the principle of marginal likelihood. Of course, it's intractable, so we would use variational inference. And all of these steps result in the variational autoencoder algorithm. And once we train this model, we have a latent representation z, which forms a smooth parametrization of the objects that we're trying to model. In this case, these are faces. So there are ways of combining this idea with autoregressive models as well. One paper that tries to do this is Pixel VAE, which combines the Pixel CNN architecture with VAEs. Essentially, a Pixel VAE is a Pixel CNN that has an additional set of latent variables z. Essentially, a Pixel VAE is the same model as a regular VAE, except that the decoder P of x given z happens to be a pixel CNN. And what do I mean by the fact that it's a pixel CNN? I just mean that it's an autoregressive model over pixels, right? So in the previous example, I just had a neural net. I had a single feed-forward neural net that, given a z, would directly print out the distribution over x. Here, the decoder is autoregressive, but the additional modification that pixel V does to a regular autoregressive model is to introduce these latent variables z, right? We still have to condition on z somehow. And in a pixel VE, we happen to condition every conditional distribution. So every p of xi given the previous xi's, we condition each of these on z. And so now that's a valid distribution of p of x given z, and we can just plug it into our variational autoencoder framework and minimize that instead of and minimize the elbow using that decoder as opposed to the one we've been using before, and it still gives us a principled algorithm. Now there's some interesting architectural details about how to actually parameterize this conditional, and this is what the figure is showing. So what the figure is showing is that the way that the decoder is parameterized is that we essentially append. So this is the image that we're trying to model. We append to it an additional set of channels which contain z. Okay, and specifically, what do I mean by this? If I were to say sample or decode from a latent code, initially that latent code is some kind of lower dimensional tensor, but it passes through a upsampling convnet, which is what we have here, to produce an upsampled tensor that's of the same width and height as the image, and it has some number of channels that we get to choose. Then this tensor gets concatenated to the regular pixel CNN layers, and then we just run standard pixel CNN on the concatenation of the image channels and the latent channels. So that's the architecture. And of course, we also have to define an encoder, and the encoder simply takes an image and applies a standard convnet to downsample it into something which looks like our Z. So this is the architecture of a pixel VE. So then the prior also, by the way, can be tuned and can be autoregressive. But the main idea of a pixel CNN is that P of x given z. Sorry, the main idea of a pixel VE is that P of x given z is a pixel CNN. And this has the advantage of having very strong log likelihoods while also learning features like a pixel CNN. So in a sense, it can combine the best of both worlds. You can also use a smaller pixel CNN to get the same result as you would get with a regular pixel CNN, right? And the reason you can do this is that a regular pixel CNN has to capture within the same neural net the entire distribution. So it has to capture all the modes of the distribution. Whereas here, our pixel VE distribution is an integral over many pixel CNNs. So it's a mixture of many pixel CNNs. Therefore, each element of the mixture doesn't have to be as big. Therefore, each pixel CNN can be effectively smaller. So that's an interesting advantage of pixel VEs. And one challenge that we have when we work with pixel VEs is that sometimes if the decoder is too powerful, then it can sometimes learn to ignore the latents, right? If a pixel CNN can model distribution even without using latents, it's possible that when you train this in practice, it will ignore the latents. And this is an actual failure mode of pixel VEs that happens in practice, and it requires extra engineering effort and extra care to avoid this failure mode. And I will again come back to this failure mode at the end of the lecture and propose an algorithmic way of dealing with this failure mode. But okay, here we have an example of how to combine autoregressive models and latent variable models. Here is also, by the way, another example. So this is not the only way in which these two model families can be combined. Again, this is not meant to be exhaustive. I'm just giving you a few examples. And here is another example that is based on a different approach. So this example assumes a different probability distribution and a different architecture for the model. So it will use a different neural net. In particular, this will use recurrent neural networks, which are a different type of autoregressive model to parameterize the autoregressive probability distribution, and using these variational RNN ideas, we will also combine latent variables into that RNN decoder. Imagine here that our task is to model a sequence of variables. In principle, this could also work for images, but this was motivated by applications like time series, where x1, xt is a sequence of variables evolving over time. A different type of parameterization of this joint distribution over all the time steps using latent variable, a different parameterization adds not one global latent variable, but one latent variable per step. So that's a different modeling choice that we can make. In the pixel CNN example, we just had one vector valued variable, but it was the same in every conditional. And the goal there is that if you're learning a distribution over an image, then you have a single representation for the entire image. Here, if you're modeling time series data, you might want to approach the problem differently and have a different latent variable per time step, because maybe at every time step, there's a different representation that is suitable for the time step, and that representation could also evolve over time. So let's say you're modeling, well, in this case, the x's are scalars, or at least in the original RNN. Although, I guess if it's a time series, the x's would be scalars, but in principle, there's nothing that forces them to be scalars. They could also be vectors. For example, imagine that you're modeling a sequence of video frames, and each frame is a separate image. Therefore, it should have its own latent variable. It makes sense that it would have its own latent variable, which evolves slowly over time. So this is the kind of task that would be more suitable to this other type of architecture. And more broadly, my point is that given different tasks, there are different ways of combining these generative models that are more appropriate for various tasks. Okay, so here, this is the way that I will choose to factorize my distribution. Again, for each, so okay, technically speaking, sorry, I slightly lied to you. In this case, all of the previous z's influence a new xt, but this could be easily modified to just only use the current zt. And yeah, so here the first term is the decoder, and again, it's autoregressive, but it depends on either one latent variable, or as in this case, on all the previous latent variables that came before time t. And in addition, these latent variables, they have their own autoregressive model, so they also evolve according to some kind of autoregressive process. So these are the modeling assumptions that I have baked into my probability distribution. Now, how do I actually model this probability distribution? How do I actually, parameterize this distribution using a neural net? Well, one way to do this is using recurrent neural nets. In this case, we have, well, in the parameterization that was proposed by the original set of authors, we have a single recurrent neural net that parameterizes both z and x. So in practice, the way this works is that there is a state, h, right? That's just a hidden state of the RNN, which evolves over time. And once we hit a new time step t, we do the following. First, we take our hidden state, and we have one dense layer that outputs the mean and variance of this distribution over z, given the current hidden state. So this gives us this variable. It gives us a distribution over this variable. Then we can take a sample from this variable, or if we're learning, we can apply the reparametrization trick to pass the resulting sample plus some noise into this component, so into the distribution of x, right? So now this is conditional on z, conditional on zt. Therefore, we can put that zt into another feed-forward neural net, which parameterizes xt as a function of the previous hidden state in this variable zt. Again, the way it gets the variable zt is via the reparametrization trick, because everything is Gaussian. So now I can sample another xt, and now that I have a new xt and a zt, I can take both of these and I can feed them into that single RNN to get a new ht, and then the process proceeds. So this is the way that sampling, I guess what I've described here is the way that sampling would work. Sorry, I kind of mixed two things. I mixed training and sampling. What I described here is how sampling would work. And at training time, you would train this using variational inference. And so you would have an encoder, which is also based on an RNN. In fact, it's based on the same RNN, which would take, so the goal here is to infer this new zt given the previous x and the previous state. And the way it could be done is by again, simply using the x, which is known at training time, and the h, which is also known at training time from the previous x's, use that to form the basis. Use these two vectors as input to an RNN, sorry, as an input to a fully connected feed-forward neural net, which outputs a distribution over this zt. So in particular, it outputs q of zt given h and xt. Okay, so hopefully this gives you at least a high-level idea of how an RNN can be used to parameterize this. I know this was a bit high-level. If you want the details, look at the paper. Here, I just want to give you the flavor of how this method works. Okay, so this is a different parameterization. Yes, so this is the particular probabilistic form of the approximate distribution. Yeah, and so this is a variational RNN. You can apply this to other type of recurrent data, or other type of data which is suitable for another regressive model like time series. Okay, so here we have looked at ways of combining these and other regressive models. What about the other type of latent variable model that we have seen, which are flows? So remember that flows are a type of latent variable model where we have the latent z and the observed variable x. Z is chosen to have the same dimensionality as x, and we use an invertible mapping f to map z to x 1-to-1. And when this is invertible, we can apply the change of variables formula to obtain an exact formula for the marginal likelihood of a data point x. And this formula involves this additional term, which is the log, which is the determinant of the Jacobian of the transformation f. So this was our flow model. And if you remember, choosing this f was a very interesting challenge. It has to be both invertible and expressive, and it has to have a tractable Jacobian. It's not obvious how to get a function to satisfy all of these three properties. One strategy that we looked at in one of the two flow lectures was to use an autoregressive model for f. So in that sense, autoregressive models and normalizing flow models are already very closely related, right? Here, I'm also proposing, well, I guess, so autoregressive models can be seen as a flow layer, and these flow layers can be stacked. And if you were to stack these flow layers, you can view each flow layer as having an autoregressive prior, which is what this slide is saying effectively. So effectively, by stacking flow layers, we're essentially assuming that the prior of layer T is an autoregressive flow. It's an autoregressive model which is specified by the flow at step T minus 1. So in this sense, flows can be seen as a way of, well, flows provide a framework for stacking autoregressive models and still have a tractable density. So that's one way in which flows and latent variable models are, and autoregressive models are related. Here is another approach. So this stacking strategy that I proposed, the stacking strategy that I proposed in this slide is a way of building a more expressive model over X. We can also use these types of flow models to build a more expressive model over the latent variable Z within another latent model. So essentially we can plug in flow models as components of other latent variable models such as VEs. Or to put it differently, we can in a sense stack VE latent variable models with flow latent variable models. Let me show you what I mean by this. First of all, let's remember the formula for the objective of a variational autoencoder, which is the evidence lower bound. So this is the way we trained a variational autoencoder. We optimized this objective, called the elbow, over the parameter space of two neural networks, the encoder Q and the decoder P. And this objective forms a lower bound on the true log likelihood. And we can rewrite the objective in terms of this additional term called the KL divergence. I just told you that the elbow is a lower bound. We can also precisely quantify the gap between the marginal log likelihood and the lower bound, and that gap happens to be precisely the KL divergence between the true posterior and the approximate posterior Q. So when we optimize over the space of parameters phi, we are trying to make this KL divergence smaller so that we end up optimizing a tighter, so that when we take gradient steps over P, we end up optimizing a tighter bound on the log likelihood. And the takeaway here is that we want to have a very expressive Q in order to make this bound tight. It's in our interest to choose Q to be an expressive model, either an expressive neural net or an expressive probabilistic model in order to make this bound tighter. In our lecture on VEs, we just made Q of Z given X be a regular Gaussian distribution conditioned on X. But similarly to how we used a more expressive decoder in the pixel VE slide, we can also use a more expressive encoder in this slide to try to make this elbow tighter by making the KL divergence smaller. So what do I mean by this? When I just defined pixel VEs, I kept Q the same. Well, I kept Q relatively simple, but I made this decoder probability a complex multimodal autoregressive distribution. If I were to also try to make this distribution Q more complex, then that would also be in my advantage, because then I could make the KL divergence smaller and I would get a better bound on the elbow. So that's another argument for why we would want to combine different generative models. So one way of combining flows and autoregressive models with VEs is to use these more complex models to parameterize the encoder of a distribution. So in particular, we could use a normalizing flow for this. Let's say that instead of only using a simple Gaussian for the decoder, right? Instead of just using a simple Gaussian like I do in a VE, let's say that I were to take a sample from that Gaussian, and then I would pass that Z prime into I would pass it through a flow layer that will output the final Z. So essentially, by composing a flow with the Gaussian that the standard VE decoder outputs, I get a more expressive probabilistic model. In the regular VE, Q of Z given X is just a Gaussian, but if I compose it with a flow, I could get a much more expressive Q of Z given X that's not Gaussian. It could be multimodal, it could have a more interesting shape, right? So P of Z given X can be a very complicated function. If I can make my Q of Z given X be more flexible, then I could probably approximate P of Z given X better. And that's one way of doing it using by applying a flow. And this is what the original paper by Razan and Mohammed did. And then Kingma et al. Further extended this idea by applying inverse autoregressive flows for this F here, right? So if you work out the math, inverse autoregressive flows are actually a really good fit here. Because we're evaluating the KL divergence under samples from the model, this is where you would want to apply an inverse autoregressive flow. And so what happens when you do this is that you can fit a much more you can essentially better fit your prior. So this is an example of the type of results that you would get if you apply the technique by Kingma et al. In this example, we're training a variational autoencoder, and our prior is a Gaussian distribution. And let's say we have 4 types of points. Each of these points gets a conditional Gaussian. So, and my prior says that taken together, all of these samples from Q should form something which looks like a Gaussian. Well, because each conditional Q of Z given X can only be a Gaussian, and let's say I have 4 data points, well, the way that the model will try to pack the samples from Q into the space of the prior is to kind of put them like this, right? But this doesn't match our prior very closely. If we were to use an inverse autoregressive flow instead, then we have the flexibility of outputting not a conditional Gaussian, but any sort of distribution. Like, for example, these little shapes here. So this little shape, and right, like we can output these slices of pizza essentially, and that fits the prior space much better. So we are able to fit the prior space much better. It clearly forms a tighter approximation to the elbow. And it's also interesting because if we were to sample from this prior, we are likely to get better samples. So for example, here, if we were to sample from the middle picture, if we happen to take samples here close to the middle of the distribution, if we were to take samples in this region, it doesn't correspond to any point. There's nothing, it's just white space. Whereas here, if we were to take samples, we're much more likely to get realistic looking data points. So fitting the prior better also helps with sampling because this is where we take samples later on. One other interesting extension of VEs are multimodal VEs. Let's say that in certain tasks, we have different modalities. Let's say that we have different types of images. We have images and their edges, or we could also have, maybe we have colored images and grayscale images, or we have images and text. So there are different modalities, but they're somehow related. Maybe, well, in the case of these colored and black and white images, clearly there's common structure. If it's images and text, there could also be some interesting common structure. In that case, we can also extend VE style models to have multiple outputs. And in this case, we want them to be conditionally independent. We want the model to extract we want the Z late variable to extract all the semantic meaning, and then everything else are purely, domain specific details that go into X1 and X2. So there's also an interesting extension of variational autoencoders, which does that. It's called multimodal VEs, and there's some interesting math that goes on if you want to compute the approximate posterior here, Q of Z given X1 and X2. It turns out that if you have a lot of modalities, there are efficient ways of doing this by applying a clever parameterization based on a mixture of experts. And so in practice, you can deal with arbitrary missing values of x1, x2 at training time, and you can do that in a principled way. It's a neat bit of mathematics. If you're interested, I encourage you to have a look at the paper. Okay, maybe one common theme in all of the methods that I described so far is that they try to combine different modeling, they combine different representations inside the same model. So flows, implicit or regressive. Another way to combine different generative models is to combine their objectives, right? So we saw many objectives that could be used to train generative models. We started with the log likelihood, but then we derived GANs, and GANs used the Jensen-Shannon divergence. And in the second lecture on GANs, we even showed that any divergence can be optimized using a GAN. So what about combining different generative models, not via their parameterization, not via their functional form, not via their representation, but via their objective? So this is an interesting experiment that can be done within a normalizing flow in particular. So remember, this is our normalizing flow. It's this bijective mapping between z and x. Because it's bijective, we have a precise formula, we have an analytical formula for the marginal likelihood at any point x. And this formula holds true regardless of how we train the model. So we can train our model using an arbitrary objective, but we can still evaluate its log likelihood. This is kind of interesting, right? We could use any divergence that we want to train this this generator, or these weights can be obtained using any process. These parameters theta can be obtained using any process, but this formula still holds, and we can evaluate the log likelihood for any choice of theta. So one interesting experiment, and this is called a flow GAN, is to train a flow model as a GAN. So a flow model is just a mapping between z and x. It's just a generator. It allows you to sample x's from z. It has the same structure. It has the same properties as a GAN generator, except that it has the extra property of being invertible, but that doesn't prevent it from being used as a generator in a GAN. So one interesting experiment that was done in a paper called flow GAN is to try to train a flow using a GAN loss. And the reason why a flow is particularly interesting for this is that once you have trained your flow as a GAN, you can still measure its likelihood. Unlike in a regular GAN where you can't measure the likelihood, here you can actually assess the likelihood of this model. So this is interesting. One reason why this is interesting is that it lets you study what happens to the log likelihood if you use a different objective. And the short answer of what happens is that when you train it as a GAN, the log likelihood diverges to infinity. So this is actually an experiment which empirically demonstrates what I told you earlier, and I gave some toy examples of why that would be true. But here, this empirically verifies the claim that I made that samples and likelihoods are highly uncorrelated. So in particular, if we were to, so first of all, we can optimize a flow GAN using an arbitrary combination of the KL divergence / likelihood and the Jensen-Shannon divergence, which is our GAN loss that's based on using a discriminator. We can optimize an arbitrary combination between the two with some parameter lambda that controls the strength of the Jensen-Shannon divergence. And what we find is that if we optimize the objective using an adversarial loss, we get the best quality samples as measured by inception score, but the likelihood is really bad. In fact, if you plot it, it can even, like in terms of just the pure value of the log likelihood, it can diverge to an absurdly large number. So this further shows how likelihood and samples are uncorrelated. And then when we train with an MLE, we get the best likelihood, but our inception score is lower. And using something like a flow GAN, we can interpolate between the two, so we can have some kind of hybrid which achieves a reasonable likelihood, but it has a lower inception score. Yeah, but I think the main takeaway of this paper is that likelihood and sample quality can be completely decorrelated for certain types of models. Okay, so here we've combined flows and GANs. Can we combine VEs and GANs? Of course we can. So here is an example of how we could do this. First, what you see here is, again, the image that illustrates the model, the probability model used by the variational autoencoder, and this is the formula for the marginal log likelihood, which is the elbow plus DKL divergence. Okay, and we can rewrite this in a slightly different form. Hold on. We can rewrite this in a slightly different form. We can rewrite this as being up to a constant DKL divergence between the data distribution and the model distribution, and DKL divergence between the approximate prior and the true prior. So you can think of this as optimizing the likelihood plus some regularizer. Now, one obvious way of combining these and GANs, and that's the first thing that anybody would try, is to just plug in the Jensen-Shannon divergence in addition to this KL divergence term. You could also add another Jensen-Shannon divergence term, so you could train using both objectives, and you will get sharper pictures. And you could also get latent variables and an encoder. So this is one way of doing it. And again, the value of doing this is that you will probably get better samples, better quality samples if you add the Jensen-Shannon term. Now, another interesting way of maybe a more subtle but also interesting way of combining GANs and VEs is to apply the Jensen-Shannon loss not in pixel space like here, but instead apply it in latent space. And that also happens to be very valuable, right? Here we're using the KL divergence. Instead of changing it on this side, can we change it here instead? If you do that, then you get a method called an adversarial autoencoder. All right, so in a VE, we optimized the likelihood plus a term that involves the KL divergence between the approximate posterior and the true prior. We can switch all the KL divergences in latent space to Jensen-Shannon divergences. And the result is that you're going to be trying to regularize the model not using the KL divergence, but using the Jensen-Shannon divergence. So you're going to try to fit your encoder using the Jensen-Shannon divergence. Why would you want to do this? Well, if you remember, I told you that, we just agreed that using a GAN loss gives you sharper images in pixel space. Well, if you use a GAN in latent space, then you also get sharper samples in prior space. And what I mean by sharper is that it matches your prior better. So this is one experiment out of many in the adversarial autoencoders paper. Here they try to fit a distribution. Here they try to fit an autoencoder, a variational autoencoder with a prior that instead of just being a simple Gaussian blob, it's this more interesting star shape. And you can see that if you train a VE, which is what we have here, it doesn't really, it tries to reproduce the star, but the KL divergence is not the best loss to use here. And similarly to how using the KL divergence in pixel space sometimes produces blurry images. Here we have something which roughly matches the star, but it doesn't match it perfectly. And if we instead were to use the Jensen-Shannon divergence or something like a GAN loss, then we get these really, then in prior space, the samples look really crisp. They very crisply match the objective they crisply match the shape that we're looking for and that we set in our prior. And there's other experiments that you can see that you can find in the paper. They use spirals and other weird shapes. So you can enforce prior regularization. You could potentially enforce prior regularization more effectively if you were to use other losses. And also it has the advantage of not assuming that Q of z given x is a prior. Remember that in the previous example with inverse autoregressive flows for the encoder, we were able to better fit the latent space by using a more expressive encoder. Here, we're also effectively using a more expressive encoder. Instead of forcing Q of z given x to be Gaussian, now Q of z given x can be an arbitrary distribution that's defined implicitly purely from samples. And as a result, you get this, you can also, I guess there's two reasons why we are able to better fit this prior. One is that we use a better loss, and the other one is that we effectively use a more expressive form for our posterior. Okay, next I want to look at the elbow a little bit more closely and come back to one point that I made earlier in the very first few slides about pixel DEs. So, okay, this is the reparametrization, this is the rewriting of the elbow that I had in the previous slide. Again, we have a term where we're matching the data distribution. We have this KL divergence-based regularizer. We can do a little bit of math here and can massage this term into something else, which will reveal some interesting structure and facts about what the elbow is optimizing for. So I'm going to do a little bit of math here. You don't have to follow this exactly, but as you can see, it's pretty short. It's just a few lines. The main point here is that we can rewrite the original objective into a single KL divergence that is a single KL divergence that takes in two distributions. One of these distributions is my model. It's my joint distribution over x and z. And notice that it has this interesting factorization. Well, in fact, I can factorize my distribution in any way that I want. So I can write it as p of x and p of z given x. You know, this is perfectly fine. This is perfectly valid. And on the other hand, I have this distribution, which I'm going to call the joint q over x and z. And I'm going to define this joint as the product of the data distribution times the approximate posterior z given x. Right? So this is the product of two distributions. One is over x, the other one is over z given x. So their product is a valid joint distribution over both x and z. And what this derivation is saying is that the elbow is the KL divergence between these two products. Okay, so far I just gave you a mathematical statement, a fact. Let's now look at why this is interesting. So this is the derivation that I just made on the previous slide. What this derivation implies is that the elbow will be optimal for any choice of Q and P that satisfies this equality. Let's look at a few ways in which we can ensure this equality. There's many ways. One way is to essentially fit, I guess one way, which is kind of degenerate and that we want to avoid, is the following. Our probability distribution can factorize as p of x given z and p of z. And now let's say that we were to simply ignore z in our decoder and we were to fit the distribution of x unconditionally. So in particular, I could imagine I was able to model my data distribution perfectly using the decoder p of x given z while ignoring the z. This is something that could happen if we were to use a really expressive decoder like the pixel CNN decoder that I had in the first few slides. So imagine this is what I learned, and then for Q, I could also just learn my approximate posterior to be independent of x and just always output the prior. So that's a really easy solution to learn. Q of z given x is just a neural net that always outputs a unit Gaussian. It completely ignores x. That's another degenerate solution. This is clearly degenerate because it's not doing latent variable inference at all, but it perfectly satisfies this condition. Therefore, this will give us a perfect elbow. All right, so this shows an interesting failure mode of VEs when you use a very expressive decoder like a pixel CNN. It shows that you can learn to completely ignore the latent variables. There's nothing wrong. There's nothing that prevents the model when it's optimized using the elbow from just ignoring the latent variables entirely. And it happens in practice for expressive models like pixel CNN and also forms of variational RNNs. When people try to create VEs from text, this was a problem that they had to deal with in practice. So there's nothing in the elbow objective that prevents this from happening. What we can do is we can try to prevent that failure mode by adding an extra regularizer. And there's an interesting line of work on using this concept of mutual information for encouraging the use of z in x by adding an extra regularizer, which is called the mutual information. So the mutual information is essentially the KL divergence between the joint distribution and the product of the marginals. So if the mutual information is 0, then it means that we're completely that z and x are completely independent, and that's what we don't want. So we're going to add mutual information into the elbow, and then we're going to try to maximize it, and that will in practice encourage the z to be used in interesting ways within the model, right? So this is a technique that is used in many models to promote the use of latent variables. It's a technique that can be combined with pixel VE or with any expressive decoder to ensure that z is used to generate x. And it was also used in other model families, not just VEs, but also general adversarial networks to introduce latent variables and encourage their use. In particular, there's this interesting word called infoGAN, which introduced an additional set of latent variables within a GAN that were meant to control the output and that were meant to produce interpretable representations within a GAN. So normally in a GAN, we sample noise and we generate X from that noise. What InfoGAN did is that they added another small latent variable, which can be 2-dimensional, 4-dimensional, and now they generate a high-dimensional noise and an extra latent variable, and they train these two things jointly. And in order to encourage the use of this additional latent variable, in order to prevent it from being ignored, they add a mutual information term between the latent variable, between the small auxiliary latent variable and the input. And what happens if you do this is that you find that the GAN naturally learns to use certain more semantic type of information within the small latent variable, and it learns to use the other variable to represent other types of noise. So, and this also, in their experiment, this led to this interesting behavior called disentanglement, where in each of the latent variables, in each of the dimension of latent variables would correspond, each of the dimensions of the low dimensional latent variables would correspond to a different property, to a different interesting factor of variation in the data, such as the pose, the lighting, shape of the face, another type of angle. So essentially, by enforcing mutual information, it's possible to get better latent variables, even potentially latent variables that are disentangled. You had a question?
I did have a question. So for example, if it's figure A, then they're only getting the variation across pose. My question is, can they get like two different representations at a time? Like variation across two different
non-distant.
yeah, basically like instead of separating one feature out, can you do it across two features?
Well, yes, but that's considered worse. Like what's happening here, maybe I didn't explain it clearly. So you have, I guess your GAN here has two sets of variables. It has running out of space for to draw. It has Z and it has this other variable called C, and then together they combine to produce X, right?
Right.
And this C is going to be low dimensional. So C will have say 4 components: C1, C2, C3, C4. Those are the 4 components of the R 4-dimensional vector C. And what happens is that, so in their experiment, if you're really careful about training, again, this is actually, there's a lot of engineering things that are going on underneath the hood, but you can potentially get C1 to correspond to only A, C2 corresponds to only B, C3 corresponds to only C, and this one corresponds to only D, something like that. Now, this is really hard to get. This is really hard, but sometimes with good enough regularization and careful hyperparameter tuning, you can get these kinds of disentangled representations. Normally, if you were to train a regular model, this would all be entangled. So you would have all of these 4 vectors, but they wouldn't correspond. You would have these 4 axes of variation, but they would all be like, if you change one component if you change C1, you change all of them at once. So that's worse.
Have they tried something like this for diffusion models? Disentanglement?
Yingheng and I, we tried.
Did it work?
Sometimes work well, but yeah, for some scenarios it can work that well, but we're just trying to add in more experiments on this.
Yeah, we should have a paper on the archive soon, but yes, this paper is under review. Yeah, so there's something that we tried for diffusion models, for example. Yeah. Cool. So this is InfoGAN, and then this idea, it also finds itself in other types of generative models, like in variational autoencoders. There's this one really simple idea, but it got a lot of attention, called the beta VE by Higgins, 2016. Their main idea of a beta VE is that you add an extra weight term on your prior regularization term, but you can show that this actually corresponds to enforcing mutual information. So if your beta is not equal to 1, like in a regular VE, that implicitly means that you're adding mutual information. So in other words, in the beta VE paper, they found empirically that tuning B can lead to better representations and even disentangled representations. And then there was a follow-up paper called InfoVE, which explained what might be going on by showing that this objective can be rewritten to look like this objective, and that actually has a mutual information term inside of it. So when you tune beta, you're actually adding mutual information. And you can see this paper for more details. And then I just want to also add with a few more thoughts on how diffusion models can be combined with all of these ideas. So one work that I want to highlight is latent diffusion, which is essentially a way of combining VEs and diffusion. Well, first of all, diffusion models are already, in a sense, a VE, but they have been successfully combined with VEs in the following way. So what this figure is showing is that, let's say that you want to generate high dimensional images. The problem with doing regular diffusion models is that you would need a pretty large UNet to model the denoising process at every step. If your image is, megapixels in size, you start to need a very large UNet. If you want to train that over a very large data set, like, hundreds of millions of images, that becomes computationally challenging, or it results in a really big model. What the latent diffusion paper proposed is that instead of modeling images in pixels, instead of running diffusion in pixel space, you can run diffusion in the latent space of a variational autoencoder. And you can essentially view the variational autoencoder as compressing the images, similarly to how you do JPEG compression. You can do VE style compression. So it takes an image, maps it to a compressed low dimensional representation, and then you generate in that low dimensional representation. So that's what a latent diffusion model is doing. So it starts with an X, and then it passes it through a VE encoder in order to get a latent Z. Then there's a forward diffusion or forward noising process that is run here to produce a ZT that comes from some arbitrary prior. And then when you generate, you sample this ZT, then you denoise it for a while until you get a denoised Z, and then you decode then you go back to pixel space at the very end with the variational autoencoder. And at each step of the denoising process, you use the same denoising UNet that you would normally use in a regular variational autoencoder, which means that you have a series of downsampling convolutional blocks and then a series of upsampling convolutional blocks. But this is more efficient, again, because this input Z will be much lower, but it will have a much smaller dimension than the original X. And what this image is also saying is that you can also easily condition this process on auxiliary inputs. If you wanted to model a conditional distribution, say maybe conditional on text, then you could have an extra encoder that encodes the text, and then the UNet can be conditioned on this embedding via an additional cross-attention layer, which is what these things are. So you can also interleave the convolutional layers in a UNet with a cross-attention layer, and that's how you would parameterize a conditional latent diffusion model. And then I guess this latent diffusion idea has been very powerful. Latent diffusion is the model that powers stable diffusion. So stable diffusion is essentially a trained version. Stable diffusion is latent diffusion trained on a very, very large data set. And it's also conditioned on these clip embeddings, which are multimodal embeddings. So this conditioning part here, it's done via this open source model from OpenAI called Clip. Clip takes text, it produces an embedding, and then you can get that, you can run the process condition on this embedding to generate really interesting imagery given a prompt. So this is the basis of how stable diffusion works. And of course, these are not the only ways of combining diffusion models and other types of models. So you can combine GANs with diffusion models. For example, there's adversarial score matching, which is a way of combining diffusion and GANs. So you know how in a diffusion model, well, in a standard diffusion model, in the standard derivation of a diffusion model, you learn the noise. But you can slightly tweak the derivation, and you will show that an equivalent way of, like an equivalent objective, it just assumes a different parameterization of there's a slightly different parameterization. Instead of parameterizing the noise, you can parameterize a clean version of the image conditioned on the noisy image, and you can train that to approximate the true clean image. So it gives you the exact, so with the same objective that you get for a diffusion model, if instead of reparameterizing the noise, you choose to reparameterize a clean version of the image, your loss will reduce to something like the L2 loss between the denoised image and the clean image. And that's just an equivalent way of formulating a diffusion model. It leads to the same objective. It just leads to a different parameterization of the probability distribution. But if you make that observation, now you might ask yourself, well, why would we be using the L2 loss for the clean image and the noisy image? Why not use the adversarial loss? So this is the idea of adversarial score matching. You can also use arbitrary losses there. So there's some interesting results there. And you can also combine regressive models with diffusion models. So one interesting connection between regressive models and diffusion models is that you can view the autoregressive process as a form of backwards process in a particular type of noising. So let's say that you have a sequence, say you have the full sentence and you generate that sentence one by one. So you can view that as a special type of forward process where your noise is to start with the full sentence and delete words one by one going left to right. Okay, so that you can view that as a trajectory that denoises the objective, that denoises the data in some way. Sorry. When you delete, you noise the data, and eventually you just get the empty set. And now your autoregressive model can be seen as trying to undo this noisy process by starting from the empty set and generating back the original words. And so that's an interesting connection that has been pointed out by a few papers. One of them is this autoregressive diffusion paper. But if you view denoising in that way, then it raises the question: well, can you have different orderings which would correspond to different types of noising processes? So instead of deleting left to right, what if you were to delete in a random order? And what if you were to just show the model sequences of clean to noisy, where the deletion is over arbitrary permutations, and these permutations are sampled at random? So if you do this, you can get any order autoregressive models, which is an older paper from 2014, or a more recent version of this with some additional tweaks is our regressive diffusion models that can that do exactly what I said. They're trained to reconstruct the sentence given an arbitrary deletion order, and as a result, they can also generate words in an arbitrary order. So you can choose to generate words according to a certain. So when you generate, you specify in which order you want to generate, and it generates it for you in that order. And you can even kind of tune the generation order as you generate. So these are additional connections between the two. I guess I'll just end by saying that we've seen a lot of basic building blocks. All of these big generative modeling families, they're not the end of generative modeling, they're the beginning. Then there's an entire literature, within generative models, you'll find many papers that try to combine these in different ways, and that results in even better diffusion models, and even better generative models. So you should be aware of that. By combining these building blocks in different ways, you get different trade-offs, and there's a lot of room for you to explore. There's a lot of research ideas that could be useful there for your projects. Okay, I'll end here and ask me any questions you have.